Welcome to our heat transfer class. We will delve in the next videos into the phenomenon of thermal energy exchange between surfaces by radiation. This video was made with the support of InnoEnergy. We know that there are three mechanisms of heat transfer: conduction, radiation, and convection. Each of them is due to different physical phenomena which allow heat transfer when there is a temperature difference. And to each of these mechanisms correspond fundamental laws that relate the heat flux to the difference in temperature. Both conduction and convection require a material medium. But what happens in a vacuum? Is energy still being transmitted between surfaces at different temperatures? Absolutely. Thanks to the mechanism of radiation, energy is transmitted between surfaces at different temperatures through vacuum or transparent media. We will divide the topic into 7 lessons. We will first study the physical phenomenon, the nature of thermal radiation, and the fundamental concepts. We will define the concept FO radiation intensity, useful tool to manage radiation heat transfer. Next, we will analyze the parameters and properties that characterize the transfer of energy between surfaces. Finally, we will build a mathematical model that allows us to predict the thermal behavior of surfaces in an enclosure. The introduction will be divided into 5 parts. But first, we are going to contextualize what is the problem that we want to solve. We will study enclosures on an industrial scale and ask ourselves the following questions. What is radiation? How is energy transmitted? How does radiation interact with matter? How can we do the energy balance? The first question deals with the physical phenomenon. What happens so that there is an exchange of energy? All surfaces at a temperature above absolute zero emit radiation. For the study of heat transfer, it is enough for us to study the emission of electromagnetic waves. Electromagnetic waves can be classified based on frequency and wavelength. The visible spectrum has no other peculiarity than that of being detected by the human eye. For the purposes of heat transfer, the area of wavelengths between 0.1 and 100 micrometers is usually considered as thermal radiation. In the problems that we will solve, in general, we will not distinguish between one zone or another. Before analyzing how radiation is transmitted, we are going to study how radiant energy is emitted. In radiation, the black body is taken as the ideal surface, which is the perfect emitter and absorber. Stefan Boltzmann's law states that the energy emitted by a black surface, per second per square meter of surface, is proportional to the 4th power of the absolute temperature. This emission is known as the total hemispheric emissive power of a black surface. Hemispheric means in all directions. Total means in all wavelengths. The proportionality is given by the Stefan Boltzmann's constant. The emissive power for a single wavelength is the spectral emissive power. Integrating this from lambda equal to 0 to infinity, the total emissive power is obtained. If we analyze the spectral emissive power, we see that the distribution curve is different depending on the temperature of the black surface. The hotter it is, the more energy it emits, and the peak of the emission shifts to shorter wavelengths. The emission spectrum of real surfaces can be compared to that of a black surface at the same temperature. Spectral emissivity is the ratio of the monochromatic emissive power of the actual surface to the monochromatic emissive power of a black surface at the same temperature. When the emissivity is constant, it is called a gray surface. The emission can be directional or diffuse. In this course, we will focus on diffuse emission, which is one in which the emission is uniformly distributed in all directions in space. The next of the questions that we have asked ourselves at the beginning is how radiation is transmitted. Radiation is the only heat transfer mechanism that propagates in a vacuum. Thanks to this, the Earth receives sunlight. In addition, it is the fastest mechanism, since it propagates at the speed of light. All this due to the disturbance of the electromagnetic field. The next of the questions that we have asked ourselves at the beginning is how radiation interacts with matter. Of the incident radiation flux, one fraction, tau, can be transmitted. Tau is the transmissivity. One fraction, alpha, is absorbed. Alpha is the absorptivity. Radiation that is neither absorbed nor transmitted is reflected. Rho is the reflectivity. As consequence of the conservation of energy, tau plus alpha plus rho equals 1. For opaque surfaces, tau is 0. The reflection can be specular or diffuse. As an emission, diffuse reflection implies that the reflected energy is uniformly distributed in all directions in space. In this course, we will work with diffuse surfaces, with diffuse emission and reflection. The final step in building a mathematical model of radiative heat transfer between surfaces is to make energy balances. We make an energy balance on the surface. The net flux is the absorbed flux minus the emission flux. Or, from another point of view, the irradiation minus the reflected flux and the emitted flux. But the calculation of the net flux of radiation on a surface requires knowing the irradiation, G. We must know what radiation flux reaches a surface from the rest of the universe. To limit the problem, we will define an enclosure of finite surfaces. The amount of radiant energy reaching surface 1 from surface 4 is evaluated with the view factor. The view factor is the fraction of radiant energy that leaves surface 4 and falls directly on surface 1. Thus, we will need the view factors between surfaces to make the radiation energy balances. Up to this point, we have made an overview of the radiation mechanism and how energy is exchanged between surfaces by this mechanism. In the following lessons, we will delve into all these aspects.